Welcome to Continuity and in Behavior. We're going to take a look at graphs that are continuous, and if they are not continuous, then we're going to look at the three types of discontinuity that can occur. We're also going to look at in behavior again, but more specifically on rational functions, whereas before we looked at polynomials. First off, what is a function that is continuous? It's continuous at a point if it is defined at that point and it passes through the point without a break. So without that break, then a function is continuous. There's no breaks in the graph. A function is discontinuous then at that point if there is a break in the graph through that point, and there's different reasons why that can occur. There's three types of discontinuity that we're going to talk about: removable, infinite, and jump discontinuity. So what is removable discontinuity? Removable discontinuity is when there's basically a hole in the graph. So one of the things we've done before is graph rational functions where the factors cancel and it creates this hole in the graph. So one of the ways that you know there's going to be a removable discontinuity is when the factors cancel. So that's how you can tell without actually graphing it. The next one is infinite discontinuity. Infinite discontinuity occurs where there are asymptotes because the graph continues on without bound. So something like this, where the graph is going to break because of that vertical asymptote. So that's where you have infinite discontinuity. And then the third one is jump. A lot of the times this happens on a piecewise function, where you might have something like this, and then there's that break in the graph, and then you have jump. So it's not just a hole, but there's space in between those values. So we have removable, infinite, and jump. So infinite occurs where you have asymptotes, and jump occurs a lot of times on piecewise functions. So those are the three types of discontinuity that we have. So we're now going to graph and determine the discontinuity of the following functions. So the first one you see is a piecewise function. Not all piecewise functions are discontinuous. We have to graph and see what's going to occur. So on the first part, we're only going to graph values that are less than -1. So at x squared, remember we kind of just create a nice little t-chart here, but we only want values that are less than -1. We want to include -1 because that's going to be an open circle there. So at -1, -1 squared is 1, -2 squared is 4, and -3 squared is 9. So at -1, 1, we'll have an open circle for now, and then -2, 4, and -3, 9. And so there's that piece. Then we have the linear equation 3x plus 4. So once again, we're going to create just a little t-chart. We're only going to do the values between -1 and 2. So at -1, it's included this time. So at -1, when you plug that in, you will get -3 plus 4 is 1. 0, you'll get 4. 1, you'll get 7. And then 2, you will have 10. At -1 and 2, they're both included. So at -1, 1, where originally it was closed, or it was open, now it is closed. And then you're at 0, 4, 1, 7, and then 2, 10. So right now it's still continuous. And then the third function is a cubic. It is just x cubed. And so on this one we'll choose values 2, 3, 4, and so on. 2 cubed is 8, 3 cubed is 27. So at 2, 8, you will have an open circle. And then since I'm on a 10 by 10 graph, it's just going to have to kind of shoot off here as you go along. And so you can see it was continuous, and now there is a break in the graph, and it's not a point that is broken. There's a jump that is occurring. So we've graphed it, and we've determined the discontinuity is jump discontinuity. So this piecewise function does have jump discontinuity, only in that one spot though. Originally it was continuous and can be continuous, you just have to graph to make sure. On the second one here, we have a rational function, so we'll have to kind of go through our process. of seeing if we can factor the top and see what happens with the bottom. Let's see, we got 3x and x, and then factors of 2 to get to 5. If we make this a 1 and this a 2, that'll give us 5x, and so therefore you have the x minus 1's canceling, and all you're left with is 3x plus 2. So since the factors cancel, we know there's going to be a point of discontinuity, and that point of discontinuity is going to occur at -1 where it's undefined, and if you plug -1 back into the simplified version, you get -3 plus 2, which is -1. So at -1, -1, there's a break in the graph. There's a hole right there, a point of discontinuity. So we know that this is removable discontinuity. And to graph this, all we have left is 3x plus 2, so we can graph that. It is linear with a slope of 3. And at that one point there is a break, so just make sure we don't graph through that. And there we go. So there's the graph, and there's the removable point. So that's removable discontinuity. Now let's take a look at 4 different functions where we're not going to graph it and we're going to identify the continuity. Now remember, it can be continuous, but if it's not continuous, be specific as to which of the 3 types it is. So you have f of x equals 5x cubed plus 2x squared minus 3x plus 4. Now when you look at this, this is a polynomial function. So it is continuous. It's a nice smooth curve, so we know it's continuous because it is a polynomial function. There's no breaks in the graph. There's no restrictions on what x can equal. So on 2a, it is a continuous function. On b, we have g of x equals x squared minus 8x plus 12 divided by x minus 2. So it is rational. So let's see if we can factor the top. We're looking for factors of positive 12. That can give us -8. So it looks like x minus 6 and x minus 2. And so we can see that the x minus 2 factor cancels. So when you have that canceling, that creates a point of discontinuity, which means if it is now discontinuous at x equals 2, it's because there's a hole there, which means it is removable discontinuity. 2c, h of x equals x minus 4 over x squared plus 7x plus 12. This one, once again, looks like it could potentially be factored. Factors of 12 that give us 7 would be x plus 3 and x plus 4. But what we'll notice on this one is this one does not cancel. So that's fine. So what's going to happen? Well, we're going to have 2 vertical asymptotes at -3 and -4. So there's going to be breaks in the graph. They're just not going to be holes anymore, which means it's not removable. They're vertical asymptotes, so they will be infinite discontinuity. Once again, because you have vertical asymptotes at x equals -3 and at x equals -4. So that's why it's infinite discontinuity. And then on part D, f of x equals, if you remember the double brackets means greatest integer function. So these were your step functions. So just by knowing that this is a step function, we know that this would be jump discontinuity. And so there are 4 examples of how you can figure out what type of continuity it is without actually graphing each of these functions. Alright, and then the last thing we're going to look at is in behavior. So we've done this before as the value... the last thing we're going to look at is in behavior. This is the value f of x approaches as x approaches negative infinity or infinity. So we're going to look at polynomial functions just as kind of a review, and then we're going to throw in a lot of rationals to make sure that we know how to find their in behavior as well. So looking at example 3a, f of x equals x cubed plus 2x squared minus 5. This is a polynomial function, so going back to your leading coefficient test, it has a degree of 3, and the leading coefficient is positive, so the shape of that is something like that. And therefore, as x goes to negative infinity, the y value is going to negative infinity, and as x goes to infinity, y value is going to infinity as well. So you're looking as x goes this way to negative infinity, what's happening to y, and as x goes to infinity, what is happening to your y value. So that is a polynomial function. So kind of a review there. Look at 3b. So this is rational. Now on this one, we don't know exactly what the graphs look like, but think about this. As x approaches infinity, what are we looking for here? As x gets really, really large, we know that on this example, the horizontal asymptote is at y equals 1/2. Why is the horizontal asymptote important? Well, no matter what this graph is going to look like, whether it's up here or below doesn't matter. As x gets really large to infinity, and as x gets really small to negative infinity, what is getting the y value? What is the y value getting closer and closer and closer to? Well, as x goes to infinity, it's getting closer and closer to that horizontal asymptote. So as x goes to negative infinity from the other side, the same thing occurs, that the function will approach the horizontal asymptote. So with a rational function, if it has a horizontal asymptote, then the graph, as x gets really large and small, the y value will get closer and closer to the horizontal asymptote. That's what a horizontal asymptote is. So that represents the end behavior of a rational function. So let's go ahead and look at C. F of x equals 5 over x squared minus 1. Once again, rational. What's the horizontal asymptote? Well, since the degree on top is smaller, the horizontal asymptote would be 0. So as x approaches negative infinity, f of x approaches 0, and as x approaches infinity, f of x approaches 0. So it's going to approach the horizontal asymptote from both sides. So go ahead and do D, E, and F on your own and see if you can figure those out. So hopefully you paused the video and did those last three. The D is a quadratic. It's opening up. It has an even degree with a positive leading coefficient. So as x goes to negative infinity, infinity, f of x both go to a positive. They're both approaching infinity. On E, the horizontal asymptote is y equals 0, once again because the degree on top is smaller. So therefore the end behavior is 0. And then on F, the horizontal asymptote with the same degrees of x to the fourth, it's 6/4 or 3/2. So once again, as x approaches infinity and negative infinity, f of x will approach 3/2. So that's the end. You have end behavior and continuity there. Make sure that as you're doing your end behavior, is it a polynomial or is it a rational where you have to check the horizontal asymptote?